Hi, it's a pleasure to have you today with us, Dr. Ying Nian Wu from UCLA, and he'll be talking to us about some of his recent research. Dr. Wu got his PhD in statistics from Harvard in 1996, and he started as an assistant professor in 97 in the Department of Statistics at the University of Michigan. He joined the University of California in Los Angeles in 1999, where he is currently a professor in the Department of Statistics. His research are in the area of statistical modeling, computing and learning with applications to computer vision. It's a pleasure to have you here.
Thank you very much.
Yeah.
Thank you for having me here. So today I'm going to talk about my recent work on cooperative learning for two types of models. One is energy-based model, and the other is latent variable model by the so-called MCMC teaching. It appears that the title may not be very informative, but what I'm trying to do is to tell you a tale of two networks. One is the so-called bottom-up network. So that is we define a probabilistic model as an energy-based model, which we call descriptor net, based on a neural network that defines energy function. And through this energy function, we then define a probability model, like the so-called energy-based model. And the other model we want to play with is the so-called latent variable model, where we use a neural network to generate the signal from the latent variables. So this is often called the generator network, which is popularized by the scan and variational autoencoder type of things. That's why we also call this descriptor net, just to match the name. And what I'm going to do today is to introduce these two types of models, and especially our recent work on these two type of models, and also how to train the two models in a cooperative way. So train the two models together so that they help each other to jumpstart their like a Markov chain Monte Carlo computation. So here I show you a diagram for neural network. As you all know, so our field has changed a lot with all those neural network. And if you go to CVPR, probably 95% of the papers are about those neural networks. Okay, so the plan is that first I will introduce some basic background, especially supervised learning and unsupervised learning and convolutional neural network, just to give you the big picture and where our work fits in. And then I will introduce our work on the energy-based model and also the latent variable model. And finally, I will talk about our recent work on cooperative learning of these two type of models. Okay, so if you have any questions, please do stop me. Just a little bit background. So there are several modes of learning, mainly three. One is supervised learning, which is the most common in CVPR community, including classification and regression. So people often train the neural network end-to-end with the label data. So you have input and output. You try to map the input to the output, learn the nonlinear mapping by the neural network. And the other form of learning is reinforcement learning, where you don't really have the output. However, you have the reward to guide you. So it is actually very similar to supervised learning. And for example, the policy network is very similar to the classification network. And the value network in reinforcement learning is actually very similar to the regression network. And then what I'm going to do today is about unsupervised learning. So that is, we only receive a large amount of unlabeled data, and we want to make sense of the data. For example, we want to learn useful features or useful representations from the data, so that later, when we bring in the labels, we can make use of those data. Actually, a more realistic setting will be a combination of supervised learning and unsupervised learning. Sometimes people call this as semi-supervised learning. So that is, you have a small amount of labeled data and you have a large amount of unlabeled data. For example, a friend of mine, Wen Ze, he's in a startup company. They have 6 billion images of faces, but most of the faces actually are not labeled. You don't know the identity of those faces. And part of the images are labeled. You know the identity. And how to make use of the unlabeled data is an important topic in semi-supervised learning and unsupervised learning. In terms of unsupervised learning, my focus will be on the so-called generative models. So that is, we want to build the so-called probability models to define the probability densities on the data. And hopefully, there are some useful features or representations in those models that can be useful for other purposes. And in terms of generative models, as the title suggests, I'm going to talk about latent variable models and energy-based models. Of course, generative models are not the only game in town in terms of unsupervised learning. There are also like embedding and autoencoding, which are also related to generative models. Okay, so these are the whole picture, and this is what our work focused. And of course, talking about learning, we cannot avoid the deep learning. For example, convolutional neural network and recurrent neural network, and also probability models with multiple layers of latent variables. So currently, I think the main success of deep learning really come from those neural networks where you can train end-to-end by this backpropagation. For other type of multi-layer models, it is still difficult to train them because of the difficulty in the computation. However, for convolutional neural network and recurrent neural network, you can always train this end-to-end, especially with those residual type of things, or LSTM. So the vanishing gradient problem has been conquered. So that can be very useful for supervised learning. And in today's talk, I will also introduce you how we make use of CNN, this convolutional neural network, for unsupervised learning. So that is, if you have unlabeled data, how to train neural network based on the unlabeled data. Okay. So just a little bit formulation about supervised learning, and then we can make transition to unsupervised learning. So in supervised learning, usually you have this type of data. For example, you have n examples, training examples. In statistical notation, we call this as a number of observations. And then for each observation, you observe a vector, the input vector. For example, a 100 by 100 image will be 10,000 input vector. And then you're also given the label output, either a continuous variable in the context of regression or a categorical variable in the context of classification. But it is often the case that you need to introduce hidden variables or features. For example, in AdaBoost, those H hidden variables are binary weight classifiers. Or in the SVM, those hidden features are actually implicit, and you have to use the kernel trick to form the product for those hidden vectors. And in neural network, those hidden vectors are not designed, but they are learned. So like this type of very simple network with only one hidden layer. But in general, there can be multiple hidden layers. And so each layer is just like a linear regression, and then followed by some nonlinear transformation. So this is a basic setup for supervised learning, including most of the supervised learning method, classification and regression. So we can use this diagram to illustrate supervised learning. So you have the input, and you generate features or hidden variables, and then you have the output, very simple structure. Okay. In terms of convolutional neural network, so it's just a very simple generalization of this very simple structure. You have multiple layers, and then this type of linear combination is changed to localized linear combination as a kernels. So they are shift invariant. You have all those filters or kernels, and each kernel is correspond to one channel. Okay, and then you have multiple layers for like a linear combination, linear filtering, and then subsampling. Sometimes also introduce some like a max pooling type of layers, and eventually you have final like a softmax classification layer. So this is what convolutional neural network is commonly used for supervised learning. Okay. And just a little bit introduction. So the CNN or ConvNet mainly is just a composition of this very simple structure. So you have the input, and then you have this filter. So the filter gives you a weighted average or weighted sum for for this input. So here, the input you have 3 channels, but later you may have multiple channels. But each one is just a linear combination. So you have this tell you the weights of the linear combination, and then you have the filter response. Okay, and then you shift the filters to different places, and you get the filter response at different places. And then you have feature map. For each filter, you have feature map. And with multiple filters, you have multiple feature maps. Okay. And then each filter here is an illustration of each filter. But when you come to this stage, you have multiple channels, a lot of channels. And then each filter involves all those multiple channels. And they are all linear combination. And then with a certain very simple, like a pointwise nonlinear transformation. Okay. Usually people use this ReLU type of thing, very simple, like a bending. So we need this type of piecewise linear bending in order to approximate the nonlinear mapping from input to the output. And when you create this bending in different places at the multiple layers, you create a very complex, highly like a nonlinear type of approximation, piecewise linear approximation with a lot of different pieces. Okay, so just a little bit notation. So for this ConvNet, we can use this notation to illustrate the mapping from the input to the output. So the input is X, and then you go over this linear transformation plus pointwise nonlinear rectification, and you have those multiple layers, L layers, and then you have this output Y hat. Based on the Y hat, you can then predict what Y is, either in the form of like a linear regression or for the softmax for classification. Okay, so that's a basic setup for supervised learning. And the recursive definition for this type of transformation is actually very simple. You have this linear transformation. This is a weight matrix, and this is a vector, and then this is a bias. And this is like a point-wise or element-wise nonlinear transformation, such as ReLU, this type of bending that I showed you. Okay, and we use theta to represent all those parameters. Okay, and in general, people use this bottom-up direction for supervised learning. And in our work, we try to take advantage of this top-down deconvolution direction in order to learn probability models. Okay, and the computation is based on this like a so-called backpropagation, where the key component of the computation is this chain rule computation that enable you to compute the gradient for the loss function with respect to the parameters. Okay. So this is just a little bit background. And from a statistical point of view, this very simple structure actually encompasses all those following statistical models. One is a generalized linear model, for example, logistic regression. The basic structure for generalized linear model is a linear combination plus a nonlinear link function. And in this case, it's just a nonlinear rectification. But I think a more meaningful way to think about neural network, especially with this ReLU type of rectification, is linear spline. For the linear spline, you have this type of thing. So that is in the one-dimensional situation, whatever nonlinear function, you can use piecewise linear function to approximate it. As long as you have enough nodes, you cut the range in a lot of different pieces, and then you use piecewise linear function to approximate it. And this is actually exactly what modern neural network is doing, except that they divide the high-dimensional space into a large number of pieces. And within each piece is a linear function, so that you have a piecewise linear function to approximate any nonlinear mapping. And this type of structure also includes this so-called classification and regression trees, or the so-called multivariate adaptive regression splines. So in these two technologies, they use recursive partitioning, but they partition the space along the axis. So each time they choose one variable to do the partition. However, in neural network, we actually partition along any directions, and those directions are actually learned. So it's much more flexible. In the early days, people feel that you just get to the local mode and your partition may not be good enough, so they use the cards. But now with big data and also with over-parameterized neural network, any local mode seems to give you a good solution. And then you have this highly with a highly nonlinear function, or rather highly piecewise linear function with a exponential many pieces, and then you can approximate any mapping. I think that's the main reason that the deep learning is so successful, because of the flexibility for approximating any nonlinear mapping. Okay. Although this type of approximation may not be very interpretable or explicit. Okay, so so much for supervised learning. And what we are trying to do is unsupervised learning. As I said before, this can be considered as a component for semi-supervised learning. So in unsupervised learning, we still have the data structure, but you don't have why. Okay? You don't observe the labels. For example, you have like billions of images of faces, but you don't know the identity for those people. And how to make use for such data to train a model for face recognition. So that's one problem, related problem. Okay, so if we don't have the output, it is like when you have the input, you have hidden layer, but you don't know what to predict. Okay, and then how do we learn the pattern or the structure in the data? So that's the problem we are trying to do. The main strategy is to build probability models on the input vector. So sometimes the input vector may be in the form of image. And then we try to build the probability models on the images. Okay, so that's the basic strategy. So just to recall that in supervised learning, you have xi, and then you have h, and then you have y, right, for prediction. But in unsupervised learning, you don't have y to predict. And then what we do, so there are two types of models. One is so-called energy-based model. So that is you have x, and then you have the feature h. Based on the features, you compute the energy. So this energy tells you how likely you observe a observation xi. So if the energy is low, that means the probability is high. Okay, so you want to learn a energy function that concentrates its low energy regions on the observed data. And in this type of learning, you cultivate all those features. So that is even without an output to guide you, you can still learn useful features based on this type of energy function. Okay? And the idea is to focus the low energy regions on the observed data. So this is one way to think about unsupervised learning. So we build our probability model based on this energy. That is, the probability of this xi is high if the corresponding energy is low. Okay, so that's the idea. And there another way of building up this model is that we treat this h as latent code or latent variables to generate this xi. So the direction is inversed. So that is, this h may follow a simple prior distribution. For example, in factor analysis, this P of h, the prior is like a Gaussian distribution, white noise distribution, very simple distribution, so that we don't need to explain this P of h any further. It is as simple as we can find. And then this P of h generates hi, and then this hi gave rise to what we observed. So that is, we now try to make sense for the observed vector in terms of latent factors that generate this. And this also gave us a good understanding for the data, so that the latent factors or hidden variables can be used for other purposes later on when we bring in the small amount of label data. And if you compare these two type models, so here h is computed in a purely bottom-up fashion. And we don't really have latent variables, and we just go to the energy function directly. And it is in this bottom-up direction, but the latent variable model is in the top-down direction. And here, how to infer this h is actually a quite a tricky problem. So that is, h cannot be computed directly from x. You need to use some inferential computations. So today, I shall talk about our recent work on these two type models. And then later we found out that you can train the two models together so that they help each other's computation. So in the energy-based model, the bottleneck of the computation is based on sampling this X from the model defined by the energy. And in the latent variable model, the bottleneck is in how to infer this hidden variable H from the observed data. And these two models can collaborate with each other. Okay, so now let me go through this. So there's another two games for unsupervised learning, maybe worth mentioning. So that one is autoencoder. So you learn. So here H, you learn a encoding direction from X to H. This is the encoding direction. So H is like you code. And then from this code, you learn a decoding direction. So the top-down is a decoding direction. So this is one way to think about the interaction between H and X. And the other way to think about this unsupervised learning is embedding. For example, in the multidimensional scaling, you want to, for each observed xi, you want to embed it in presumably a lower dimensional space, so that this hi capture the relationship between xi. For example, in the multidimensional scaling, you want this hi, a low dimensional embedding, to preserve the relative distance between those observations. And in the local linear embedding, you also want to preserve some local structures. Okay, so the probability models can actually be interpreted from these two perspectives. Okay, so but now we try to make use of the convolutional neural network to charge both the energy-based model and the latent variable model, in the sense that for the energy-based model, for the input signal X, for example, image or video, our energy is defined by this F function. And this F function is parameterized by a neural network. Because, as I said before, the neural network is a piecewise linear function, which is a very powerful approximator, approximating any mapping, nonlinear mapping. So we take advantage of this strong approximation capacity to define the energy function. And in the top-down convolutional network, so in this so-called latent variable model, the mapping from the latent variables to the signal is also characterized or parameterized by a top-down neural network. Okay, so that's where we introduce the neural network to our work. Okay. So now let me go to this energy-based model, what we call the descriptor net, just for simplicity. So here we use a multiple layer of neural network to define this energy function. Okay, and then the probability distribution for the observed image can be defined in terms of this energy function. And this P0 is just a reference distribution. You can use a uniform distribution, but in our case, we also use a Gaussian distribution, a very simple distribution as a reference, or like almost like a prior. And then you try to tilt or modify this distribution into this distribution. So this f of x is almost like a likelihood ratio, the log of the ratio between p and p0. But f can also be interpreted in terms of the energy function. So that is energy function in this case is basically just a negative of log of the probability density function. And in that case, if we use Gaussian white noise as a reference, then the energy function is this part. This comes from the Gaussian part, and this is from this f, where we are going to parameterize by neural network. Okay. So this is a simple form for energy-based model. The one difficulty with this type of model is that
you learn S as well.
X is observed. We observe a lot of examples of X. S we fix X. Yeah. Presumably, S you can also treat S as a parameter. You can also learn from the data. But in our case, we just fix S as a certain value to make this almost like a uniform. And then we learn this theta. Theta include all the weight and the bias parameters in the neural network that characterize this F. So the difficulty with this type of model is this Z. Z is a normalizing constant. So that is you integrate this whole thing over the high-dimensional space of X. And it is usually analytically not tractable. Okay? And the computation of Z and its derivative become a quite a difficult problem in this business, in this energy-based model. Okay? But other than that, if you can learn this model, learn this data, then automatically you learn all those features, even without any output to guide you. Okay. So we can also connect this to the discriminative net, because if you do classification, then often you use this softmax type of classification. So the idea is that if you have a neural network and you generate K, suppose you have K categories, capital K categories, 10 categories, and you generate 10 score functions, 10 function F. They may share the lower parameters, weights, but with different heights for different categories. So if each category is parameterized by this model, and you also include this P0 as a negative category, then a simple application of the Bayes rule give you this posterior probability. You assume some prior probabilities on those categories, and then given each category, the probability of the observed data follow this energy-based model, and then the posterior probability for category K given the observed data is based on this softmax. So therefore, this energy-based model directly corresponds to the commonly used convolutional neural network for classification. So that's maybe a justification for this type of model. So that is, after you learn the models, you may actually make use of the small amount of label data for classification purposes. Okay. And if you don't have labels, then you may have to learn it in unsupervised fashion. So that is, we observe Xi from a distribution, I call this P data, that generates the data, generates those Xi. N is the number of observations, and we don't have the label. So what we want to do is to model the observed data by a probability distribution defined by such a function, often called Gibbs distribution or the Boltzmann distribution. And this one, as I said before, is defined by these two terms. But if you use uniform distribution for the reference, then this energy function is simply the negative of this F.
So do you postulate what F is?
F is a neural network, yes. We parameterize.
So mechanically, you have all these parameters.
Mm-hmm.
And then
Right.
how do you construct F
With
all the parameters?
Based on a neural network. So here, with this one, right, we have this bottom-up thing. So suppose you have this final layer, and then a linear combination of those things give you this F. And then this F consists of multiple layers for weights and bias parameters. So you parameterize this transformation by a neural network, which is approximation to the nonlinear mapping. So we use neural network mainly because it is very flexible, like approximation to any nonlinear mapping.
Okay, maybe we can talk about it later.
Yes. Yeah. Okay, and then we need to learn those parameters in the neural network. So what we do is to use the log likelihood and to learn maximum likelihood estimate. So the idea is we want to find theta to maximize this function. In other words, we want to find the most plausible explanation for the observed data in the context of our model. Okay? Because if this is big, then the probability of observed data is very big. So that is, we want our model to put very high probability on the observed data. Okay? And this one actually is related to minimizing the so-called Q-bilateral divergence from the data distribution to the model distribution. You can think of this as a projection from the data distribution to the family of models. You can imagine that each distribution is a point, and then the family of the model, by changing the parameters, is like a manifold of some sort. And then you project your data distribution to this manifold. So that is the closest distribution you can find to the data distribution. Okay. And then in order to use gradient descent for learning theta, which is a common thing to do in a neural network, we need to take a derivative. And here the derivative is in this form, which is the derivative for this energy function with respect to theta. And this is from observed data. But this term actually is from the model. So basically, you look at the difference between the observed data and the model, what's predicted by the model, as far as those derivatives are concerned. And then you update your theta based on the difference between the observed data and the model. Okay. The reason that the maximum likelihood has this derivative is that the log of z has a derivative. The derivative of log z is exactly the expectation under this model. So that's a commonly used result in Gibbs distribution. Okay. And then you need to sample the data from the model, because the difficulty with this part is that the expectation cannot be computed analytically. Okay. So what we did is to use Monte Carlo method. We sample those synthesis data or imagined data from the current model. Okay. And how do we do that? We use a so-called Markov chain Monte Carlo method. We use this long-driven dynamics. So we start from a random white noise image, and then we run a gradient descent on this energy function. But then we also add this noise term to account for randomness. So this gave us the sampling. If you don't have this term, you just go to the local mode. With this term, so you are doing this random sampling. So you sample from the current model using this dynamics. Okay. And then you generate the synthesis data. It's like you close your eyes and fantasizing what the model tell you. For example, you want to learn a model cat, and then you imagine what the cat look like, given your current model. Okay. And then this become your synthesis data. I use Xtutor to represent the imagined data. And then you update your parameter based on the difference between the imagined data and observed data. Okay, you can think of this step as almost like dreaming. You dream what, say, a cat look like. And then you look at the difference. So if your dream is not very realistic, you update your parameters based on this gradient. Okay, until these two things, they match each other. Okay. So this is actually an analysis by synthesis scheme. So that is, we synthesize data from the model, and then we update our parameter based on the difference between synthesis data and observed data. Okay. And you can also have an adversarial interpretation of this learning algorithm. So that is, you want your energy to be low on the observed data. Okay. But relative to what? Relative to the synthesis data. So you can think of this as a value. And this sampling method, I use this called long-driven revision, because this is long-driven dynamics. Keep revising x tau. Tau is a time step in the inner loop for generating the data from the model. Okay. So this sampling step try to decrease. Try to increase this guy. Okay. And the density shifting step try to decrease this guy. Okay. So the idea is that the general idea is that you try to shift your probability distribution from the synthesis data towards the observed data. Okay. So that's the main idea. Okay. And then eventually your synthesis data will match the observed data. And in this calculation, we need this derivative for updating our weight parameters in the neural network. And we also need this derivative for sampling the images. But these two derivatives, actually, they are based on the same, like a chain rule calculation. So it is automatically given from this TensorFlow or any like a neural network software. Okay. Now let me show you maybe some result. Okay. So this is like a diagram for this analysis by synthesis scheme. So we have the descriptor network, the energy-based model. So you use long-driven dynamics. I call this D1, D for descriptor. So you use this long-term dynamics to generate synthesis examples. And then based on the difference between synthesis examples and observed examples, you update your parameter. So that's a scheme that we are doing. So you can think of D1 step is like dreaming. The model is dreaming. And D2 step is to make the dream come true, to make the dream more realistic. Yeah. And so here I show you a few examples. So this image is observed image. Okay. And we want to learn a probability model. And those images are generated from the learned model. Okay. So somehow the model appeared to capture some like appearance for the observed image. And this is another example, this observed image. Those three images are sampled from our model using this long-term dynamics. That is by running gradient descent on the energy function and also add the perturbations. Okay. The same with this example. And there's some other examples. Again, the first column consists of observed examples, and the other columns are the synthesis examples. So here, we learn each model from a single image. There may be some issue of overfitting. Okay. And also, we try to learn from the object, images. So the left are some of the observed images, and the right are images generated by the model. So apparently the model dream up the pattern, okay, gradually updating its parameter and to make the dreamed pattern or fantasized pattern getting close to the observed pattern. This is still a small data situation. And then we try to scale up to learn bigger data. For example, SLM A data set, which consists of tens of thousands for face images. And in order to speed up its computation, we use this multi-grade scheme. So we try to learn model at multiple grades. And then when we do the synthesis, when we sample from the model, we start from like a 1 by 1 pixel, 1 by 1 image, which is the smallest image you can think of. Okay. And then we upscale to 4 by 4, 16 by 16, and this is 64 by 64. So the training images are 64 by 64. And then we can scale up the learning to relatively big data set, including a bedroom data set with 3 million images. So currently with the GPU, the computation is actually quite efficient. For example, a single second, we can generate 100 images from the model. So the sampling can be done quite efficiently. So in this sampling step, we go through 3 stages. And each stage, we use 30 steps of long-term dynamics. And then this is actually very efficient. And then it can generate all those patterns very easily. And those are some other examples. And we also try this on this cipher data set. So those are the images generated from different categories of the cipher data set. And we also evaluate our method using this inception score. And I don't know whether this is actually a good measure. Some people actually wrote paper saying that the inception score may not be the right thing to do. But anyhow, so our inception score is comparable to the DC GAN reported by another paper, okay, although we use a completely different method. And then we can learn features from the data, from the unlabeled data. So here we did some experiment on learning features, and then later use those features for supervised learning after you bring in a small amount of labels. Okay, so this is from this SV whatever, the house number data. Again, it's quite a big data. And those are the observed images, and those are the images generated by our model, dreamed up by our model. And we use this SVHN. I couldn't remember those names. And then we use the learn the features. And after that, we bring in some labels, and we train a classifier. And we compare our method with some other methods, including WGAN, and also DC GAN, and some other deep directed generative models. It seems that the features learned by our method in unsupervised way gave reasonable performance. And we also did semi-supervised learning. So that is, we train our network and learn the features from a large amount of unlabeled data. And then we use some labeled data to train another convolutional neural network on top of the learned features from our model. Okay, so this is a commonly used method for semi-supervised learning, and we compare our method with some other methods reported in the literature, and it appears that our model, this generative model, indeed learn reasonable features, useful features that can be used later on when you have labeled data. Okay, so here the semi-supervised learning I think is quite common in nowadays, because a lot of data are actually unlabeled data, and labeling the data is quite expensive. So rather you want to label a small amount of data, but a lot of data remain unlabeled, and you want to make use of the unlabeled data and to help you to learn a classifier later on. Not only classifier, we can also learn a model as a prior model, and then we can use this for phase completion. For example, this is the original phase unobserved, and this is a blocked phase. And then we can sample the pixel values of the blocked part, given the observed part, the visible part. Because if you know the probability distribution, the conditional distribution is automatically defined. And you can sample from such a conditional distribution to recover the phase images. So that is, the learned model can be useful for image processing purpose. And we also check the error and compare this with some other related model fitting method. And it appears that the multi-grid learning method perform quite reasonable. Okay, so this is the energy-based model. Now let me move on to the latent variable model. So actually, those latent variable models are all generalizations for previous model that based on this linear structure. So that is, you have those latent variables, and you want to use those latent variables to explain the observed vector. And the traditional model, for example, factor analysis, all based on this very simple linear structure. So that is, the observed vector is a linear transformation of the latent vector. Okay, and people call these latent variables as factors in the factor analysis, or sources in the independent component analysis. Or code a lot of names, because this type of model is very commonly used in many different disciplines. And you can also interpret this W in different ways. You can think of this as a loading matrix. So that is, each input variable is a linear combination of latent factors. So this is like a loading. But you can also think of this as a superposition of basis vectors. So that is, each column is like a vector, and you superpose those vectors, so that each vector is almost like a word in a dictionary. So that's the view adopted by the sparse coding. And then you can also think of this thing from the perspective of matrix factorization. So you have n observations, you can factorize them into W and this H. And this view is commonly adopted in this recommender system, and also non-negative matrix factorization. And people often call this type of representation as a distributed representation, because this is not one hot. You are not doing clustering. Rather, you distribute the factors into different dimensions. And it's a dense representation. It's not sparse. And also people use the word embedding. That is, we embed this vector in this latent space, or disentanglement. So that is also latent factors disentangle the variations of the data. Okay, and the traditional factor analysis is a very simple form. You have this HI follow a very simple IID Gaussian distribution, which means you don't need to further expand this HI. Each HI is a vector. Okay, S observation, and Xi is another vector. For example, four-dimensional vector. Based on a linear superposition of those factors in HI. Okay. And often we assume that the dimension of this one is smaller than this one, although this graph is different, but sometimes people assume that this is actually a smaller dimension. And then this gives us a dimension reduction, similar to the so-called principal component analysis. And There are a lot of work to generalize this type of model. Most of the generalizations in the past is along the direction of generalizing the prior distribution, okay, the prior distribution of H. So for example, if you make this H to be non-Gaussian but independent, you get independent component analysis. And if you want to make this H to be sparse, that is a lot of components of this H vector are zero, then you get the sparse coding, or so-called sparse component analysis. And you can also introduce a positive constraint on the component of H. And then you get this non-negative matrix factorization. And also this restrictive Boltzmann machine or denoising autoencoder, they can all be considered as generalizations for factor analysis. But they generalize this prior model, basically. Okay. Another way of generalization is to generalize this linear mapping. Instead of using this like a linear mapping, we can use nonlinear mapping. And what can be better than a convolutional neural network, which is so flexible? So that's the idea of the so-called generator network. Okay. So that is, in order to make it deep, we use this direction. So you can think of this as your H. You feed your H to a top-down neural network to generate the image. So this is reverse order. Okay. In the Euro classification network, you do this from image to class label. But here you have the latent code, H, latent vector. And you use this H to generate your observed image. Okay. So that's the basic idea of generator network. And people actually use this initially in the supervised setting. So that is, you have this top-down generator network. So here we use alpha to represent those weight and bias parameters of this neural network. So this, from H, is a top-down. You go to the image with multiple layers for like latent variables. And in this learning, they actually they are given this H. H is given. You know what type of chairs you are using, and also the viewing angle or some other geometric parameters. And then you can learn a mapping. And then you can interpolate this mapping. So you have two different H. You can interpolate this H and then generate this X, so that you can change. You can look at the change of the chair in this interpolation space. Yeah. But then later, people also use the GAN or VEE, generative adversarial network, or variational autoencoder, to study this problem in a purely unsupervised way. So that is, H is unobserved. It follows a prior distribution, very simple prior distribution, the same as in factor analysis. The only difference is that we make this linear mapping to a nonlinear mapping. Goes through a top-down neural network. Okay, so that is, feed this H to a top-down neural network from this H, and then you go to multiple layers of H to get this observed image. Okay, and we develop a very simple method for fitting this type of neural network. So the idea is that we have this loss function. We want this H to expand the data, but H is unobserved. So you only need to alternating two steps. For each observed image, you infer this H by a gradient descent method on this loss function. Okay, and after that, you can learn your parameter alpha based on the inferred H. Because after you infer H, it is almost like a supervised learning. And then you can continue to use this gradient descent to infer your parameters. Okay, so this type of method actually also based on this like a derivative computations with respect to alpha and also with respect to H. And both gradient can be readily computed based on the existing software. Okay. A more like a rigorous justification is based on this EM algorithm type of justification. So that is, we have the joint distribution in this form, which you have the prior, and then you have the conditional. And then you want to maximize the marginal likelihood. And this involves two steps. One is the inference step. Instead of using gradient descent, again, you need to add noise to account for the uncertainty, because the posterior distribution of H may contain the uncertainty. And after you infer H by this long-driven dynamics, you can learn from this imputed data. Then given H and X, then alpha can be updated by gradient descent on the reconstruction error. Okay. And we actually learn a generative network from small data first, as we did for the energy-based model. So this is observed image, and this is generated from the learned model. Now the generation becomes very simple. You just generate H from a normal prior distribution and feed H to a top-down network. Then you directly get the image. You don't even need to use any Langevin or Monte Carlo sampling, okay, iterative sampling. So this is based on the direct sampling. Okay. Again, those are other examples. This observed image, this is the image generated by our model. Okay. And we also fit the model on a small sample for like a tiger and lines. And you can see that we only use two-dimensional H. And then we can plot the generated image. And you can see how a line changed to a tiger rather smoothly. And for the face, we also did similar things. And those are the generated from the model. And you can see the interpolation result, how a man changed to a woman if you change in the H space. So the mapping is highly nonlinear. So a linear interpolation in the H space gives you highly nonlinear mapping in the original space. Okay. And we can also learn this from highly incomplete data. So you only need to change this term by summing over the visible pixels. Okay. And then you can learn this, you can infer H. After you infer H and learn the parameters, you can recover the images. So those are the training images. Those are unobserved. So we learn the model directly from the incomplete images. So this type of model seems to be quite powerful. And we also compare this with principal component analysis. You can think of principal component analysis as a linear dimension reduction. But this one gives you nonlinear dimension reduction. And we compare this on the reconstruction error on the testing data. And it has a smaller error. And also you can see that for the PCA, this line is a principal component analysis. It gives you rather blurry reconstruction. But using this nonlinear dimension reduction, it is a little bit sharper. Okay. And we can also learn a representation where different viewpoints share the same H, but different network. And then using this learned model, you can change the viewpoint. So you feed in this image, and then you ask which viewpoint you want. And then from this one, you infer your H, and then feed this H into the network corresponding to that viewpoint. So this is the ground truth, and this is recovered by our model. So this type of network seems to be quite flexible to capture those a rather nonlinear change in the viewpoint. Okay. And now we come to this cooperation. So in this cooperative learning, we try to train these two models together. Okay. So the idea is that we use this descriptive network as a teacher and the generator network as a student. Okay. So the student write the initial draft. The student can easily generate the images just by generating the H from the prior distribution and feed H to the top-down network. You generate the image. Okay. And then the teacher then revise it by sampling using the gradient descent on the energy function. Because this energy-based model, you can revise this generated image by a gradient descent on the energy model plus some noise, okay, to account for uncertainty or randomness, okay. And then the student can learn from this revision, okay. But the point is that the teacher now has a very easy way to jumpstart this MCMC, okay. So that is the student provides the initialization of the Markov chain Monte Carlo for sampling the energy-based model. And at the same time, the student can learn how this Markov chain Monte Carlo revise the sample is generated. Okay. So that's the cooperative learning. Okay. So that is a student learn from the revision by the teacher. Maybe this diagram may capture this basic idea. So in the original learning method for the energy-based model, we generate synthesis example. This is a bottleneck. So MCM sampling of the synthesis example can be time-consuming. Okay, but now we use the generator to provide initialization of this one. Okay, and but in this in this learning of a generator model, we need to infer the latent factor. So this inference part is a bottleneck for the generator network. Okay. And what we did is to combine them. Okay. So maybe I use this diagram. So the idea is that the generator generates the initial, first generates the latent factors. And then it gives us an initial synthesis example. And then the descriptor run Markov Monte Carlo from this initial synthesis example to get the revised synthesis example. Okay. After that, based on the difference between the dreamed up example and the observed example, the descriptor can update its parameter. More importantly, the generator does not need to learn from the observed example. The generator only needs to learn from the synthesis example. So this is the initial synthesis example, and this is a revised example. So the difference tells us how to update the generator. Why this learning is good? Because in this learning scheme, the generator knows the latent factors. Okay. The generator generates the latent factor itself. So the latent factors are already known to the generator. So this is unlike the observed examples. Yeah, I will try to wrap up. Okay. So the basic scheme is like this. So we have the latent variables, latent vector, and the latent vector generate the initial example. We then run MCMC based on the energy-based model, basically gradient descent on the energy. Okay. And then from this H, the generated H, and this X, revised X, we update the generator network. Okay. A more rigorous version is you start the inference dynamics of this H from this generated H. So this is a more rigorous method. But often we use this one. It seems to work good enough. And you can think of this as MCMC teaching. So the idea is that this is the initial example, and your MCMC is going toward this energy-based model. And then after this updating, you do the projection to update your like a generator network. So this way you can train your generator network. This is teacher, so this how teacher train this generator network to be closer to itself. Okay. So we call this as the MCMC teaching. So the idea basically is that when you run the Markov Monte Carlo, you have those Markov transitions. You want to update your generator network by changing its parameters to account for the transition, to absorb the transition, or to memorize the MCMC transition, and then reproduce the MCMC transitions in one step. Okay. So those are the examples. Again, the first column are the observed examples, and those are the synthesis examples. And then we also studied it, tried this on the like slib A data set on the faces. So those are the generated faces. And then we also tried this on ImageNet. So there's 10 scene categories in ImageNet. We put them together and we learn this model. So the image on the left are the observed images, and the image on the right are the images generated by our model. And also we can do the interpolation. So you can see the change from one scene to another very smoothly by just interpolating on the H, the generator. And we compare this with DC GAN, generative adversarial network, in terms of like inception score, and also the like a faithfulness for the generated images. Just we compare on some of the measures, and apparently is doing better. And we again compare this inception score to like evaluate the quality of generated images and compare with some other GAN method. Initially, we didn't want to do that, but the reviewers keep asking for comparisons, and more comparisons, never ending. And also, we try to do this pattern completion for the recovery. So if you block part of the image, whether you can recover. And we compare this with DC GAN on the recovery, and also some traditional method. So here are some recovery results. So those are unobserved ground truths, and those are the images we observed given to the model. And the model can recover the blocked pixels. And this is another example of image recovery. So I think it's hard to measure whether it's a good recovery or not, because you cannot just measure the difference between the ground truth and the recovered in this case, unlike face. For example, for this one, you see this observed image, right? It blocked this part. And then the recovered image actually sampled a window. It still makes sense, although it's not the original ground truth. But somehow it appears that the model indeed remember a lot of information from the data. And here are some other image syntheses. The left are the observed images, and right are the generated images. Okay, now I just want to wrap up. So here we use a lot of like a neural network parameterization. So basically, it's just a piece like a layered linear operation plus a minimum nonlinear, like a bending type of nonlinearity. So I still feel very uncomfortable actually with this type of neural network. But somehow it seems to be so flexible. You can use this to approximate any like a mapping, so that you can learn representation. You can also learn computation. Basically, a computation, so the solution to a computation problem can also be learned by a neural network. But my uneasiness comes from the fact that this is convolutional neural network. You have over-parameterized model. It's hard to interpret. It's totally a black box. Even though it is powerful, we really don't know what we are doing. But somehow, I don't know whether this is the fact that we have to accept. One example analogy. Yeah, one example is quantum mechanics. Nowadays, we still don't know what the quantum mechanics is telling us. It's a black box, basically. But it gave us those correct probabilities. People still try to interpret it and argue whether there's like a multiverse or multi-word, many-word interpretation. So we still don't know the interpretation, but we just use it, shut up and calculate. And here, maybe we just shut up and doing this computation. But I feel it's very uncomfortable about this type of things. So still, I think we want to build more interpretable models, especially at the upper layers, so that we have more logical or grammatic understanding, such as the AND/OR graph that my colleague Song-Chun Zhu has been promoting and Tianfu has been working on. So this is the type of model I hope that eventually we may develop, not just this black box. So somehow I had some fun with this black box thing, but I don't feel quite happy about this type of model. And also, frankly, I feel a little bit bored by this thing. It seemed to be too successful. You can build this 100-layer network to approximate everything. What's the point? Nowadays, for the CVPR, I told myself, I'm teaching a course on computer vision. And I tell them, if you read the CVPR paper, look at figure 1, you know what this paper is doing. Look at figure 2, you know what the network is about. And no need to read anything else. So the paper becomes so similar. And also, you just increase your data and make your network bigger and use a lot of GPU, you get a result. But this seems to be so unscientific, so I don't know whether we can go beyond this stage. But somehow this is like a phase maybe for what we have been doing. Yeah, I may just stop here and take some questions.
Any questions?
Yes?
Yeah, I had a question on your generative model. Have you investigated what is the diversity of the samples it generates?
Yeah, we investigate that. That's actually a very good question. Because in GAN, there's a very serious mode collapsing problem. So GAN gives you extremely sharp, realistic images, but it's really underfitting. It fits part of the data, but it totally ignores other part of data. So we try to compare this diversity. And indeed, actually in one graph, we actually compare this diversity explicitly. We look at the pairwise difference, and our diversity is much bigger than the DC GAN diversity.
Even in high resolution?
Yeah, even in high resolution, yeah. So therefore, you think about this model fitting, this underfitting issue. So indeed, GAN give you very sharp things. But if you look at the generated image, recently people actually did some like a comparison. So if you generate a few hundred images, then you can easily find 2 images that are almost similar to each other. So this is a very serious underfitting problem.
Yeah, the question.
I had another question.
Yes.
So in your last, the cooperative learning,
Uh-huh.
so the updates for the generator and the synthesized image, so those are all constrained optimizations.
No, not really. It's still based on the original algorithm, except that for the generator, you train the generator based on the synthesis data.
Mm-hmm.
Because the synthesis data, you know the latent variables.
Yeah, but
So
you wanted to constrain the KL divergence between the next distribution and the existing.
Yeah, we try to minimize the KL divergence. Yeah.
Okay.
So this actually lead to a interesting interpretation in that the generator try to be the stationary distribution of the MCMC Markov chain for sampling the energy-based model. And then it's getting close to the energy-based model. Yeah. But the energy-based model, there's a bottleneck for the synthesis. The generator provides this direct sampler. So you can think of the generator as a sampler of the energy-based model, so that you don't need to use iterative MCMC. You use this neural network to directly sample from this model. Yeah. So that means the boundary between representation and computation is really blurred. So for whatever computation problem, you can always train a neural network as your solution. You directly target your solution. Do not need to do any optimization. At least online computation can be avoided. Yeah.
So did you have any problems in terms of your convergence to basically the wrong
Yeah. So
local minimum?
yes, that's the issue with neural network. So people call this alchemy, right?
Well, I reserve I take the fifth.
We always go to a local minimum.
Yeah.
Yeah. And
But
indeed,
sometimes it works, sometimes it doesn't. That's the
Yes,
problem.
yeah.
And
so in our case, often a local minimum seem to be okay. But I know that for a student of mine who's working on this, he actually talked to his friends in NVIDIA. They said they train 1,000 models, and then they select the best one. So therefore, you go to 1,000 local minimum, you try to select the best one. There are so many GPUs, they can afford that. We cannot. We train one model and we just use it. Yeah. But indeed, we don't seem to understand very much about the local minimum. Although there's some common myths or legends saying that all the local minimum are about the same if your model is heavily over-parameterized. And there are also some theoretical investigation apparently supporting that. But still, I think sometimes if you run the model from different starting points, you get quite a different performance. Yeah. That's why in the company, when they have more GPUs, they can beat you in performance. They always choose the best one, right? They can afford to run 1,000 models, train 1,000 models, choose the best one. Yeah. It's hard to compete with them.
all right, if there are no more questions, let's thank our speaker.